In the last video, one of the theorems that we saw was this one right here that says if two functions are continuous at a value a, then their sum is continuous there, the difference is continuous. We can also multiply one of them by a constant, and that's continuous. Their product is continuous, and the quotient is continuous, so long as g of a is not equal to 0. So basically, when we take two functions that are continuous at a certain value, we can add them, subtract them, multiply, and divide them, so long as we don't get a 0 in the denominator. And the resulting functions are going to be continuous at that value a. And if these are continuous for all real numbers, then the results are also continuous for all real numbers, unless we have a 0 in the denominator. We always have to, be careful about that. But I want to prove one part of this theorem for you, because we haven't done too many proofs, and this is not a difficult one to do. So specifically, I want to look at this first part that says if two functions are continuous at a certain value, the sum of those functions gives us a continuous function at that same value a. So to prove this, we need to think about what we actually need to prove. If we want to show that f plus g is continuous at a, we must show that the limit as x approaches a of the function f plus g of x is simply equal to the function f plus g evaluated at a. Because that's what continuity at a point means. It means that the limit of the function at that value, as x approaches that value, is just equal to the function evaluated at that value. All right, so let's take a look at the limit as x approaches a of f plus g of x. Now, we can also write this as the limit as x approaches a of f of x plus g of x. That's what f plus g of x means. It's the sum of those functions. Now, we know that when we take the limit of a sum, that is equal to the sum of the limits, so long as those limits exist. So this is equal to the limit as x approaches a of f of x plus the limit as x approaches a of g of x. That is from a limit law that we have seen before. Now, if we look at each of these limits, remember the thing that we were given in this theorem, the given was that f and g are continuous at a. And remember, the definition of a function being continuous at a value is that the limit of the function as x approaches that value is simply the function evaluated at that value. So because f of x is continuous at a, that means the limit of f of x as x approaches a is just f of a. And similarly, because g of x is continuous at a, that means that the limit as x approaches a of g of x is equal to g of a. Because these functions are continuous, we can evaluate the limits by just evaluating the functions at a. And then f of a plus g of a is another way to write f plus g of a. And so in the end, we've shown that the limit as x approaches a of f plus g of x is equal to f plus g of a, which is the definition of that function being continuous at a. If we can evaluate the limit by just plugging in that value, that means it is continuous at a, and so we have proven that f plus g is continuous at a. If you wanted to do a really nice write-up of this proof, you would want to explain written down why each step is true. I verbally explained why each step was true, but if you were going to be taking advanced math classes with proofs, because maybe you're going to be a math major, you would be expected to write out a lot more. You'd be expected to write out an explanation for why each step is correct. but it takes a long time to write while you're recording a video, so I just said those things verbally. But just want anyone who's watching this, especially if you're skipping ahead to the end, to know that there is a lot of explanation for why each step is true, different limit laws and theorems that we've already seen. And so it's important to include those if you're ever writing up a formal proof. There you go.